Okay, so the question is about the cruise performance. And let's first go through the question itself. For an aircraft weighing 50 kilonewton and having a wing area of 26 square meters, and this question has 4 sub-questions. So let's go to A. We are asked to calculate the value of CL, lift coefficient, which must be provided by the wing for flights in international standard atmosphere conditions at indicated airspeeds of 100 knot, 150 knot, and 200 knots. So basically the question is to calculate the CL to sustain the indicated airspeed of 3 speeds. Okay, so let's see how can we work this out. Because it's in cruise, and we have the information of weight 50 kilonewton and the area 26 meter square. And we know it's in cruise level flight, so the lift should equal the weight, and in the same time lift can be calculated as half rho v square times s times the lift coefficient. That's just a definition. Okay, so by having these two relations, we can have the lift equals weight, and then since we are asked to calculate CL, so if we just write CL explicit, and then CL is 2W over rho v square times s. We have the weight W, and also we know the speed, and also we know the area S, and we don't know the density. So how can we figure out the density? That's a question. And probably you already noticed I highlighted indicated airspeeds in the question itself. So what does that mean? If it is indicated airspeed, so we should use the density at sea level. So all the indicated airspeed were calculated using the sea level density. So in the CL equal to W over rho v squared times S, the density should be sea level density, which is 1.225 kilogram per meters cube. Okay. And now we need to convert the speed from knot to meter per second. So 1 knot is 0.5144 meter per second. And then 100 knot is 51.44 meter per second. So we just plug in a number into CL and also the density. Then we can have the lift coefficient, which is 1.187. And for the others indicated airspeed, which is 150 knots and 200 knots, we just do the same procedure. Well, 150 knots is 77.16 meter per second. Then the lift coefficient 0.527. And if it's 200 knots, the speed is 102.88 meter per second. The CL is 0.297. So we can see with increasing indicated airspeed, the CL decreases. Now let's look at the second part of the question B. If the value of CL remains constant at 0.314 during cruising flight, then at what true airspeed and Mach number must the aircraft fly to maintain straight and a level flight at altitudes of 0 feet, 100 feet, 1,000 feet, 5,000 feet, 10,000 feet, and 20,000 feet? So now we are asked to calculate the true airspeed to maintain the CL and also the Mach number. So the difference is the true airspeed instead of indicated airspeed. Okay, so again at sea level, let's first calculate the altitude flying at altitude of 0 feet. That's at sea level. The density we already know is 1.225 kilogram per meter cube. And again, we can write down the lift definition, and also we just write velocity. This is true airspeed. Explicit is square root 2L divided by rho SCL. And because it's a level flight, L equals W, we just replace L by W. And now we can see we have the W, which is a weight. We know the density at sea level, and we know the area, and also we know the lift coefficient. We can just get the true airspeed, which is 100 meters per second. Okay, so now let's work on the other heights. I already listed the answer in here, and because we know with the increasing altitude, the density also changes. So for each individual altitude, we need to look up the ISA table, International Standard Atmosphere, to find the density at each altitude. So that's a practice for you to do, and you should use the linear interpolation to find the density at each altitude, and then we just replace the density in the above formula, and we can get the true airspeed at each different height. And we can see with same constant CL, and if the altitude increases, the true airspeed also increases. Yeah. So when the increased altitude and true airspeed increases under the same CL. Now let's ask, what about the indicated airspeed with different height? Will the indicated airspeed change? The answer is no, it won't change, because for indicated airspeed, we are using rho 0, which is the sea level in that formula. So if rho is replaced by rho 0, and it doesn't change. And because also CL doesn't change, L doesn't change, area doesn't change. So indicated airspeed, despite the change of altitude, it doesn't change. So in order to answer this question, we should know the difference between indicated airspeed and a true airspeed. The second part of the question B is to calculate the Mach number. And we know if we want to get the Mach number, we need to have the speed of sound. Actually, because Mach number is a ratio between true airspeed and the speed of sound. And at sea level, the speed of sound is 340.29 meters per second. And we can get this from the ISA table. So at sea level, the Mach number flying at 0 feet height is 0.29. And in order to get the Mach number for the other altitude, we need to again look up the ISA table. So following the same method, we can get the other Mach numbers at the increasing altitude. And we can see the Mach number actually increases with increasing altitude on the same CL. The question C, the third question, is if the value of CL max is 1.35 with flaps retracted, so we are not using the flaps, we are asked at what true airspeed will it store at altitudes of 0 feet, 100,000 feet, 5,000 feet, 10,000 feet, 20,000 feet. Okay, again, it's actually the similar question as B, because we are fixing the CL max. Okay, so let's first have a bit understanding about the question. So the question actually asked about the stall speed, and the stall speed happens when CL maximum is achieved. If we look at the CL angle of attack curve, which is on the right hand side, we can see before store happens or before the CL max is achieved, we can approximate the curve as a linear change with the CL and the angle of attack. And after the CL max, that's a store happening. We have flow separation, and so with increasing angle of attack, the CL actually decreases. So the on the CL max, we have the store speed, or its definition of the store speed. And again, we can have the weight equals a lift, and in this condition, the lift is calculated as a store condition or critical point of the store where the CL max is achieved, and we denote store speed as Vs. And then we can calculate Vs as this relation. Okay, so we know W in this relation, we know W, we know CL max, and also at different altitudes, we know the density, and of course, we know the wing area S. So since we've already looked up the table, get the density at these 5 altitudes, and then we can easily get the store speed. And the store speed, true airspeed at store, increases with increasing altitude. And there's a question, how about the indicated airspeed at store with increasing altitude? Or how the critical airspeed, how the indicated airspeed of stores changes with increasing altitude? The answer is it will remain constant, because to calculate the indicated airspeed, we need to use rho zero. That's the density at sea level. So because in the square root, everything is a constant, and the store speed of indicated airspeed is a constant. This is what we need to remember. The last part of the question D is, if the value of CL maximum is 2.7, it's doubled with flaps fully extended. So at high lift configuration, the CL max is 2.7, is doubled from earlier. Then at what true airspeed will it store at altitude of 0, 100,000 feet, and 5,000 feet? It's actually a similar question, and just with a changing increase the CL max. Again, store speed happens when CL max is achieved, and we have the same relation as in C, right? And so actually we've already again have the density at 0, 1,000 feet, and 5,000 feet. We can have the store speed, and this is a true airspeed, and which is smaller than in question C, because this time CL is increased.